Welcome everyone to the second session of the intuitive introduction to machine learning. I'll quickly recap what we did the last time. We looked into the definition of machine learning, to the question, what is learning? What is intelligence? And we came to the conclusion, to the understanding that the evidence of intelligence is ability to learn. Now, the ability to learn is a quantifiable measure. Science deals with measurables, things that you can quantify. And the way you quantify learning in machines or in human beings is through an error function. You can quantify how wrong you are. For example, we took the example of taking a child to a meadow which has cows and ducks and just asking the child, what is this? Is it a cow? Is it a duck? And counting how often the child is right and how often the child is wrong. When the child doesn't know the distinction between a cow and a duck, there would be a baseline error rate. Half the time the child would be wrong because the child is simply guessing. On the other hand, as you gradually see and you educate the child, and as you gradually see a progressively correct answers coming by, correct identification, the errors go down, the error rate goes down. Learning is quite literally the process of decreasing errors. One question that I didn't address is, can there be perfect learning? In other words, can a machine be 100% accurate? I would like to start by addressing that question because that's an important question. See, suppose you have a data and you train a machine on a data. Day before yesterday, we mentioned that any data is a sample of the reality, sample of the population. You never really have access to the entire data set, for example, you cannot line up all human beings in the world just to find what's the average height. What you would do is take a sample of human beings and take the average. In the same way, when you train machines or you train human beings, they can become very, very good on your data, the data that you train with. The question remains, does that necessarily mean that your model would work just as well on unseen data? So for example, you show on a meadow all the cows and ducks, and your child becomes very good at identifying cows and ducks. The question remains, how do you know that the child hasn't just memorized, doesn't have photographic memory, and memorized all the cows and ducks? And all that the child is saying is, okay, I remember seeing this animal and it was labeled cow, so I'll call it cow, without understanding what a cow is. And the way that you do that is you keep some data under the pillow, a test data set, which you never show the model, you never show the child or the machine. So you'll keep some cows and ducks or some section of the meadow that the child hasn't visited. And then if you feel that the child has learned, you take your child to that part of the meadow and show those animals then and ask, what are these? If your child is still getting the same rate of correct answers, you feel that your child has learned. The word learning is also closely associated with the concept of generalization. What your child has done is, by seeing a few examples, your child has generalized the concept of cows and ducks, has formed a concept, a model in her mind of what a cow is, the essential cowness of a cow, the essential duckiness of a duck. The child has grasped. And because the child has grasped that, the child will now use that model, mental model, to look at an unseen example and be able to tell whether it's a cow or duck. And her prediction accuracy, her identification accuracy would be as good as a model. For example, let us say that just happen chance, all the cows that you showed to your child in this, when you were explaining cows, were all black cows. And let's say that all the ducks that you showed were all, let's say, light colored ducks. What your child might have accidentally learned is black is cow, light is duck, color-wise. So when you take your child to a different part of the meadow, where it so happens that you have brown cows and white cows, and you have brown ducks and dark ducks, now your child will start making mistake. And so where is that mistake coming from? The child will still be able to identify black cows as cows and light colored ducks as ducks. You say that the model, the mental model that the child has formed is flawed. Likewise, in the machine, the model that has been learned, that the machine has learned is flawed. It needs more learning. The converse of that question is, can a model always be perfect? In principle, yes. In theory, yes. If it has really actually grasped the concept. But in practice, it doesn't happen because data invariably comes with something called irreducible noise. So in real life example, if you show your child a cow, which is really, really far off on the horizon, and ask the child, what is that? Child may squint and see there's a small animal out there, might not realize that things look small at a distance, and might legitimately say, we are looking at a duck. Right? So those mistakes can happen still. It doesn't, so the absence of perfection does not mean that your machine or your child hasn't learned. This is something to remember about. There is a term that's often used about machine learning models, and I'll lay it. Machine learning models make probable. They're probably approximately correct, always. And the probably approximately correct, for me, quantifies the essence of machine learning models. All of you who have played with machine learning have seen that. Most of you are now playing with chatbots, ChatGPT, Gemini, things like that. And you must have noticed that most of the time it probably is correct or approximately correct, but it does hallucinate. It does give wrong answers occasionally. So there is a certain error rate. It's just that despite the error rate, you nevertheless find the machine useful. It's something to remember about AI. That the goal of AI is not perfection. There is a famous saying by a data scientist, a statistician, whose name was a box. And we will have some entertaining stories to tell about Box and his brother-in-law named, of all things, Cox. And they in fact wrote papers together called Box Cox. And those papers became celebrated papers. One of the most celebrated results in statistics is the Box Cox transform. In machine learning is the Box Cox transform. We won't cover it today as an intuitive intro, but Box said something very appropriate in this field. He said that all machine learning models are wrong. All models are wrong, but some are useful. He said it about statistics, but today statistics and machine learning are the same discipline. So the goal is not to build perfect models. There is no definition of correct, but of utility and usefulness. Is it useful? Just like all of you use ChatGPT or something, and those are useful tools. So utility is the measure in this field. Well, today, with that out of the way, we talked about one more thing. We talked about center limit theorem. Why is it that we can get away by taking just statistical samples and still be able to tell something about the entire population, which you will never conceivably encounter? Much as we try, we are not going to shake hands with or go measure every single human being on planet Earth. Nevertheless, we get a pretty good idea of the average height of human beings simply by taking samples. And to that, we refer to the center limit theorem. In the lab today, we will do some example. We'll just see how remarkably well the center limit theorem works. If it weren't true, we couldn't have learned from samples. Right? We couldn't have extrapolated from samples to generalize from samples. So the topic today actually is something called, it's a negative word, it's called regression. Today is going to be a little longish session, folks. I must warn you. We are going to do first the theory and then lab on computer. So I hope you all have your laptop. Today I'll also help you set up your laptop if you do have it. But I'll do the setup at the very end. So we'll first do theory, we'll do lab, and then we'll do setup. And then the code that I will walk you through, we will release it. We'll have to find some vehicle. There's a course portal which all of you can self-register to, and on that course portal you'll find all the code. So rest assured that any code I show you is there on the course portal already. So the word regression, let's look into the word regression. Regression is the converse of to regress, like especially those of you who are engineers. What happens when you notice that your application has regressed or there are regression bugs? It's not a very thrilling news. It means things have gone wrong. Isn't it? Something that was working isn't working anymore. So ironically, this word has stuck for historical reasons to one of the most important algorithms, a class of algorithms in machine learning. And regress, of course, is the opposite of progress, opposite of progress or progression. How in the world did such a negative word come about? And it has to do with a very interesting observation by one of the earliest, what today you would call data scientists, Galton. Galton observed that if you look at children of very, very tall people, I believe he first studied it in peas and then he saw that in humans. So and his famous paper was with peas. He noticed that if you look at the height of, actually, no, it was with humans. So if you look at the height of very, very tall people, their children tend to be little less tall. You would expect they would be even taller if Mr. Tall and Mrs. Tall get married. They have the tall genes. And their kid potentially will be even taller. Actually, it doesn't work that way. What happens is Mr. Tall and Mrs. Tall will end up producing, or Mr. Tallest, Mrs. Tallest will end up producing a child who is a little bit shorter than the parents. Likewise, if you go to the other extreme, if you look at Mr. Shortest and Mrs. Shortest, and you look at their kid, you would observe that they're actually taller than the parents. So why is that? And it turns out that the reason for that, I leave you as a puzzle to figure out after you have learned what we have to teach. And that is why, because the reason for that comes from this algorithm or this thing that we are going to learn today. Therefore, it is true. At some point, if I don't explain the answer, I'll let you hold that puzzle in your mind. But if I don't explain the answer, remind me, and I will do that. But suffice is to say that because the explanation lies with this, the name has stuck. Galton's disciple was Pearson. Pearson of the Pearson correlation fame. Correlation that we studied in the last session was the work of Pearson. So there's a lot of history out here, but I'll skip that and I'll go strictly to the definition of regression. So from here onwards, we are in the territory of supervised learning. In supervised learning, you're given an input and you have to predict an output. And imagine that there is some machinery, and all machinery in machine learning are nothing but functions. They're very complicated functions, the functions that you can't understand possibly. For example, a neural network is such a complicated function that you cannot write it down on a piece of paper. It's a bizarrely complicated function. Nevertheless, they are functions. So a supervised learning is an algorithm, which is basically this. If you give it an input, it will produce what is called a prediction. Now, predictions in machine learning wear a hat, generally. You want to distinguish it from the ground truth. So suppose I told you that, let's say, you have a stone, right? I give you this stone, you know its size, and I ask you to guess its mass. Right? What would you do? You would have some internal formula in your mind. You would say, well, the density of this white stone is probably this much. Therefore, if I know the size, I can multiply the size by the density, the volume by the density, and I would have the mass. Does it make sense, guys? I could do that. So that mental picture that translates of size to a mass of this stone is your model. It's a regression model that you have in your mind. Are we together? Now it is dependent upon the volume. And if I show you a different stone, let's say I show you a different stone now, and you might say, this looks different. I happen to know that this looks like, let us say, a granite. It's likely to be heavier. So you have a different density in your mind. And so you'll apply a different density to it and come up with it. Are we together? So from the color, what you have is from the color and the volume, you are able to first internally come up with a way to compute the mass of it. But those masses, let's say input is volume, and volume you have to guess because I'm just showing it to you. Right? But suppose I tell you the volume, I tell you it's so many cubic centimeters. Then, given the volume, there is a mass that is the ground truth. I happen to know what the mass is because I have the scales here next to me. Imagine that I have a scales here. I don't have it actually, but imagine that I have a scale here. So that would be what we call the ground truth. The ground truth. But your guess, you as a regression model, your mental model of it is a prediction. Prediction is given, again, made to wear a hat. And so I can have some data, x1, there would be a mass to it, y1, and there would be a prediction to it, y1 prediction. Do you see, guys? We have a triplet, an input data, a ground truth output, and you're asking to make a machine that predicts the mass. So input goes in, size, color. I tell you these two things, right? And you have a box. The box produces a guess, an estimate, a prediction, y hat, which is the mass of the stone. Does this make sense, guys? Now I can compare that mass with the ground truth because I happen to have weighed the stone. Right? And because I have a jar of stones, right? There are lots of input volumes, colors, and lots of masses, and you have to make an estimate for all of them. Now, let us say that all of your estimates are widely wrong. What can you tell about your mental model? There's a huge scope for improvement. On the other hand, suppose I do this. I give you one stone, tell you the color and the mass, right? And you make a prediction. And let's say that you predict y hat is 75 grams, right? And the ground truth was, let's say 50 grams. Then what can I do? I can tell you, oops, you were wrong. It was actually 50. So what can you do from these two? You can compute the error, which would be y minus y hat. Isn't it, guys? That is the measure of the error that we made. And what can we do from the error now? We can say, hey, maybe I need to recalibrate my internal calculation. Maybe it's not as dense. This color is not as dense as I thought. So if I decrease the weight, my density factor in my model, I will have better prediction. Are we together? That is called learning in machine learning. That literally is learning. And the way that you would say here, I took a very, very simple model. The only thing that you're trying to figure out is, given the color, probably the size wouldn't matter, but given the color, what possible material it is, and therefore what's the density? The density, the density that this model has, density, let me just call it D, density, D, is a model parameter, isn't it? It is your understanding that for white, this is the density. For black, that's the density. Are you right? And so you will have density D1, D2, D3. Let's say that there are 4 colored stones. Stones of 4 possible colors. Actually, that happens to be true. White, gray, nice, what color is it? Brown. Brown, and black. I do have 4 colored stones in my jar. So you would just think of 4 densities. And every time I showed you a stone and I told you the volume, a white stone, you would say, white stone, what is the density for the white? This is it. And use that to multiply the size to predict the mass. If the mass is more, if your prediction is more than the ground truth, because I'll tell you the ground truth, you will decrease the density. Every time you underestimate, you'll increase the density, isn't it? So what you say is what in this very simple example, what we call densities in machine learning, there's a fancier name. These are called, usually written as theta, parameters, because mathematicians love Greek characters. No wonder when they talk, people say these guys are talking Greek. Okay, parameters. These are parameters of the model, right? Because this is part of your own mental model, isn't it? You happen to know the physics formula that mass is density times volume, right? And all you need to do is guess the density by color, right? And you make an internal presumption, hypothesis, that you can essentially guess the material by the color it is, that all white colored stones come from the same material. So what are all of these? These are your internal hypotheses, isn't it? So a model is a hypothesis. It's a mathematical hypothesis. It's a way of relating the input to the output. So now I hope you understand that. And by the way, look at the input. Was the input just one variable? No, it is two things, size and color. Size is a number. Color is a label, isn't it? So you can have categorical in these things that have finite set of values, like say, what are the four color values we took? White, black, brown, right? And gray. So input can take values, the color can take values only amongst these four. You call these things color as a category and each of the color values as a class, typically. It's sort of the vocabulary in this field, but we can dispense with the vocabulary. Suffice is to say that the input can come predominantly, there are many ways of doing it, but traditionally inputs come as numbers. Numbers could be integer numbers or floating point numbers, or they could be as categorical variables, white, black, brown, gray as color. But in regression, the output is always a number. So you say when a machine, when y hat is equal to fx and y hat belongs to a number. Actually, for those of you who are well trained in machine learning, you may want to say it's a d-dimensional number, a vector, but let us dispense with those, dispense with being too correct for the sake of getting understanding the facts. So if it is a number, a machine that can predict a number is a regression machine, a regressor. Right? It's regressing. It's a regression algorithm, or it's a regression model, or it's a regression machine. For example, if a machine could tell what's going to be the temperature tomorrow at noon here in Fremont, temperature is a number or is it a kind? It's a number. Therefore, that machine is a regression model. It has a regression model that it is using. This is important. Now, that is the context for today. What other things could it produce? Go back to our example, cows and ducks. If you ask a child, look at that animal. It's big, right? It has these characteristics. It has horns and all these properties. Those are all inputs, isn't it? The output is what? It's not a number. The output is a label. You're saying, is it a cow or is it a duck? Or another way of saying, the output is categorical. It takes one of two values, cows or ducks. And maybe if you bring in horses also into your middle, then it takes one of three values, cow, duck, or horse. Are we together? So that is the concept. So those machines, so let me put it this way, a machine that produces, given X, produces a Y hat, which happens to be a number, is called regression. By the way, this R with the unnecessary bar that you see here, this is a mathematician's way of saying a real number, a number that takes value from minus infinity to plus infinity. Right? It need not be in that range. For example, you are unlikely to have stones that are infinitely heavy, because then I wouldn't have been able to hold it. Right? You couldn't have stone whose mass is negative also. But nevertheless, we say that it is some part of the real number line. Now, if you don't remember the real number line, it's just a number, some number that can be a fraction also. That's a number. On the other hand, if you give it an input, x, and it tells y hat, tells a class, you call it a G, a class, predicts a class within a category. This is the formal word people use. I will just call it tells, in intuitive terms, tells whether it is a cow or duck. These algorithms are not regression algorithms. They are making correct prediction of what that animal is, but these are called classifiers. These are classifiers. So these are two very important characteristics. Now, it turns out that these are the workhorses of the AI world, actually. Your weather modeling is a regression problem. Your ocean currents is a regression problem, right? Revenue estimation in a company is a regression problem. Whether, like, how much the GDP will grow and whether or not interest rates should be cut or not is a regression problem for the economists. Right? On the other hand, classification problems are all over. You take an X-ray of your chest, and whether or not there is a tumor present, benign or cancerous, malignant, whether or not there is a tumor at all, is a classification problem. Right? Whether any anomaly is present or not is a classification problem. If an anomaly is present, what kind of anomaly there is itself is a classification problem. Is there a scarring tissue? Is there a tumor? Benign tumor? Is there a malignant tumor? Is there a liquid filling up the lungs? Things like that. Right? Those are all from a list of potential things that could go wrong with your chest. You're picking one or saying everything is clear. That's a classification problem. When you use your chatbot, oh my goodness, that is an AI engine. What is it? Regression or classification? Every time you ask it a question, for example, you ask it a question like, what is the capital of California? And it comes up with an answer. Now think through, is it a regression problem or a classification problem? That's a tricky one, actually. Not so easy to guess. You've just gotten introduced to this. Or is it an entirely different class of problems than the simple ones I'm talking about? Any guess? Actually, we call it a classification problem for a very interesting reason. When you ask a chatbot, a large language model, a question, all it does is it says what it has is a vocabulary. Let's say a vocabulary with words from odd, what, all the way to, let's say the last word. I don't know what the last word in the dictionary is and what the first word is, but I'll pretend aardvark to zephyr is a pretty good way of looking at it. Let us say that this vocabulary is, let's take a simplified vocabulary, 10,000 words. So when you give it a question, what is the capital? The machine gets it. All it has to do is pick a word from the dictionary and say it is the first. All it does is it doesn't actually answer the question. It just answers with one word from the dictionary. When you pick, this is it, a word. Is that from a finite set? Dictionary is a finite dictionary of 10,000 words. Is that regression or is that classification? It's a classification. It's the same thing as telling it's a cow or duck. Right? You identify, you pick one from enumerated list. Dictionary is a classic, vocabulary is a classic enumerated list. So it will pick the word the. So now what you do is you take the and you feed it in here. And now you feed this new input. Remember, this was the initial X. Now the new X is X1. This was X0, right? Is the new input to your machine. It now again has to classify. What does it have to do? Pick the next word. And then it may say, it might produce a sentence that is the capital of California is Sacramento. But what is it doing? It is running a classification algorithm. How many times? 1, 2, 3, 4, 5, 6. 6 times. Are we together? And then maybe 7 times for full stop and an 8th time end. Because after it is done, it needs to, there's a special word end. End. Don't say anymore. Just say I'm done. Right? There's a special token you keep saying, I'm done talking. So your chatbots also are actually within the category of regression and classification. You can reformulate it and think about it. And that's why they're called the next token prediction engines, next word prediction engines, these large language models. So, well, today we are talking about regression, and I'll motivate regression. Again, I'll just recap what we learned. In regression, an input goes in. Input could be one dimensional, or think about it this way. It could be one column of data, 2 columns of data, more columns of data, right? So when data comes across as multi-column, let's say when you're looking at the stone, it is its size and its color. So to describe it, you would write it as 2 columns, isn't it? You say it has 2 features, right? Or it is a 2-dimensional data, right? That's the way that you would think about it. So it doesn't, and that's why quite often you represent input with a vector. But if you're not familiar with vectors, you can sort of gloss over it. So we agree that this will produce regression algorithm is nothing but machine to somehow internally, mentally form some function in its mind, some hypothesis of the relationship between input and output. That's all it is. I'll give you, just to pin this idea into your mind, I'll give another illustration. Let's say that a young fellow decides to open an ice cream shack on the beach. Well, summers are coming. I'm looking forward to beach tomorrow. So I think beach must be in my mind. So now you want to open an ice cream shack. What does she have to do? She goes and opens an ice cream shack. But ice cream, if you run the shack from morning to evening, when do you have the time to make the ice cream? You don't. So you're going to, or maybe you do, maybe you'll make it at night. But the one thing you need to guess, how much ice cream to make or to buy from the wholesaler, isn't it? Ice cream is a perishable good. It is not something that you can hold on to for a long time. So we will assume that she serves ice cream only fresh. What does she have to do? First thing is she has to guess how much ice cream will sell on the beach tomorrow, isn't it? As an entrepreneur, she doesn't want to make too much ice cream, and she wouldn't want to make too little ice cream either, because if she makes too little ice cream, she'll have the unenviable pleasure of just sitting in her shack watching the competitor ice cream shack getting all the business, all the kids going to the competitor shack. Not a pleasant sight, so she would want to have her own fair share of kids coming to her shack. So what she does is she starts observing what does traffic, kids traffic or beach traffic depend upon. I suppose when it comes to ice cream, we are all kids. So what she does is she realizes that temperature matters. It seems that temperature, let's take one factor, temperature. On warm days, you tend to sell more ice cream, right? Or her competitor is selling more ice cream or whatever, or she herself sells more ice cream. So she starts collecting data gradually. And let's say her data is like this. And let's say that the day becomes extraordinarily hot and people don't come anymore. Actually, traffic dips. What have you found? What has she found? Let's say that this is the ice cream zone. Let's call this variable y. Let's call this variable x. Temperature is the input. Because temperature is something, she can look up the weather prediction. We all pretty much have a good weather prediction for the next day these days. So temperature becomes the input. Now she can decide how much ice cream will it sell. But you realize that this data is just some points of data. For her to get a very accurate, for example, she doesn't know on this temperature, there is no data. So what can she do? Intuition says that you can build a model. She can build a model. If she hand draws this curve through the data, now she can use a curve to estimate how much ice cream will sell. Does that make sense, guys? What is this curve? What is geometrically a curve is a function algebraically. or in AI, we'll call it a regression. So far, so good, guys? So that is the value of coming up with a regression model, a function that can predict that from the data, because then you can generalize for any temperature value for which you don't have data now, you can predict or estimate how much ice cream is needed. So how do you know that you're completely off? What if perchance she doesn't see the obvious, but she makes a model. She makes a model like this, the red model. How many of you would, so let me call the red model B and the blue model A. Now, which of the two models would you consider to be a better model to estimate the ice cream? You would always say it is A, but why would you say that it is A? Intuitively, when you look at it visually at the data, why would you say that A is a better model than B is? Anybody? Especially those of you, there's a lot of people on Zoom, I noticed. Would anybody like to venture? Why is A a better model than B?
Because the number of ice cream sold as predicted by the model is closer to the actual
value. So what you're basically saying is the same thing that we talked about a little while ago. The prediction of the curve, the prediction of the y hat minus y is likely to be smaller than y hat minus y of the red model, isn't it? The errors on average is less, right? Average error. But errors could be positive or negative. You could have overestimated or underestimated, isn't it? Look at the red line. At some places it grossly overestimates, at some places it grossly underestimates. But so does the blue line, right? So how do you quantify error? Remember, machine learning. For example, a journey to go from a B model to A model would be a journey of learning, isn't it? A machine learning, that's what it is. It makes less mistake. So let's quantify the errors. We could start by saying for every point, I could, irrespective of the model, whatever the model is, I could do this. This is the, in other words, suppose you have the errors. I define error of every error of prediction to be y hat I, y minus y hat. Traditionally, it's written like this, y hat I. This is the error. So you could say that I could just do a measure how wrong a model is by just summing the errors. Does that look fair? But there's a problem with that. Can somebody spot the problem with this? Quantifying errors like this.
The errors might be like really positive and negative, sum to zero at the end.
Yes, excellent. Excellent. So you're saying the same thing.
My point was the same.
Yeah.
Meaning in some instances the error would be very large, and in some instances it's going to be very small.
And it could be positive, an underestimation error, overestimation error, and they can all cancel out. But clearly, nevertheless, still A is better than B. So what you can do is not look at the error, but you can look at the absolute value of the error. Now, overestimation error and underestimation error, both of them are just errors, and they can add up, isn't it? You can sum all of these errors. So now it turns out that you can compute error this way, and if you have n points, you could say, so this is called sum absolute error. And if you divide it by, actually, let's divide it by the number of points, because then you will get a sense of average underestimation or overestimation error, right? So then it becomes mean absolute error. It has a famous, it is a famous term that is abbreviated as MAE. But remember, I told you the story of Carl Friedrich Gauss. One of the observations that the great mathematician made is that while this is a good thing to use, an even better thing that you could use is you square it. When you square, you don't have to take the absolute value. You realize that because square of numbers is positive anyway. Square of errors is positive anyway. Right? Why is squaring a good idea? It turns out that he and Markov are credited with a famous theorem called, which we won't go into, Gauss-Markov theorem, which we won't go into. And people who do business or economics, etc., they are taught about it in a slightly different manner. In econometrics, it's called the blue theorem, which has quite an expansion. Best linear, unbiased estimator. Let's try to deconstruct that very, very long phrase. Estimator, a model, a synonym for a model is an estimator. Now you say unbiased. Did we encounter the definition of biased versus unbiased last time? We did, right? So average, of course, is an unbiased. But it is unbiased in a, well, there's more nuances to it. I won't go into it. Linear, when you build linear models, for linear models, especially when you're trying to fit straight lines, it is the best linear unbiased estimator when you try to minimize the square of the errors. Are we together? And here's the basic intuition. When see, small errors squared, square of small numbers is not that big, but square of big errors is really big. So what squaring the error does, it blows up huge mistakes, makes it stand out. And therefore, when the machine learns, it has to first learn to fix big mistakes, and then it fixes smaller mistakes or tries to fix smaller mistakes. So first priority goes to big mistakes. That's the real reason that works better. But this is a famous mean squared error. Why is it mean squared error? Square, you literally see the square. Mean, you literally see us taking the average. It is called the MSE. And in regression, it is perhaps the most, therefore, because of the Gauss-Markov theorem, it is actually the most used metric. You start with MSE and you force the machine to somehow learn to reduce the MSE and become better. Are we together? Now the whole question is, well, it is very nice to say that somehow reduce, but what does somehow mean? How? How do you teach a machine? You realize that problem remains. How does a machine learn to make lesser and lesser errors? There has to be a process. And I'll give you the intuition behind that process. It is something that, it is the opposite of what common sense says. Right? It is called gradient. Listen, see, when you're hiking and you're going up a hill and you have reached the top, right? You want to come down. Generally, is it a wise idea to take the steepest part down? No, you're likely to break your bones. So you actually try to take a circuitous route. Right? So imagine a very steep mountain. What will you do? You will go like this, like this, like this, and gradually come down. But you would nevertheless agree that if you want to come here, the shortest path is this path, isn't it? Now you say, what has that to do with minimizing errors? So the explanation for that is very interesting. See, let's write the error function. And this is a little bit of mathematics I would like to do because it is because the learning in machine learning is almost always done through gradient descent. The reason these large language models are talking to you today is because they have learned through gradient descent. It's a very powerful algorithm. So it's worth knowing the basic idea behind gradient descent. Right? And if the mathematics is obtuse, then you can sort of skip over it, or maybe take a gloss over the fact. It doesn't really matter, but it is nevertheless fun to try to explain it, and I'm going to do that. See, suppose you have data. Let's take the simplest model that you can build through some data. It would be some straight line, isn't it? This is your model. A model is a function, isn't it? Yx. Y is fx. The prediction is fx. Are we together? Now, what is that function? If you have been through high school, you would say, it is mx plus b. It's the equation of a line. It has an intercept. This part is b, and slope is m. Slope is m, isn't it? Now, in machine learning language, you don't use m's and b's. You tend to use Greek letters. People are fond of Greek letters. So you write it as theta naught plus theta 1 x. This is theta naught and this is theta 1. It's just a change of notation. Nothing deep is achieved. It's just a convention that in machine learning language, we tend to use Greek letters for parameters because theta naught and theta 1, intercept and slope, define a line. If your hypothesis changes, let's say it's this pink line, but then it has a different intercept and different slope, different parameters, isn't it? So in some sense, you can say, give me the best line that goes to the data, which is the same as saying, give me the best parameters, which minimize the error. Do you see, guys? I'll write these two statements and ponder over it. Give me the best line to the data is the same as give me the best line that minimizes errors, isn't it? Right, most proximate. So let's write the error function, which we agreed was 1 over n times sum over all the errors. Right? What was the error? Y minus y hat. Predict the ground truth versus the prediction. Right? Squared. But what is y hat? This is ignore the I subscripts because in the beginning it might be theta naught minus theta 1 xi square. So the error is written as a function. E is now, look at this, it's a summation over I. I'll just rewrite it here. Theta naught minus theta 1 xi square. Now guys, when you're training the machine on data is fixed, isn't it? Data is not changing. You're trying to find the best parameters that fits the model. So therefore the error is a function not of data, but of parameters, isn't it? Data is fixed, xi, yi are fixed. So E is a function of theta naught, theta 1, isn't it? You're trying to learn the best parameters, slope and intercept, that will minimize the errors, putting it very simply. Are we together so far, guys? Right? So now, if this is a function, and observe that this is a quadratic function, quadratic in theta naught, theta 1. If you expand it out, the highest term will be theta naught square and theta 1 xi square. Theta 1 square, xi square, isn't it? These are quadratic in theta 1, theta naught, and theta 1. Do we see that, guys, or should I expand and show it? We all know how to multiply these two terms. It will be quadratic. Now, what is the typical? Now, also you realize that it is the sum of squares. Sum of squares, is it fair to say that it has to be greater than 0? Now, do we remember from school days, what is a quadratic function which never becomes negative? What's the simplest quadratic function you can think? What about something like this? An upward facing parabola. And because we are talking about 3 dimensions, because they are theta naught, theta, so there's error. This is theta naught, theta 1. What happens is this error is actually, it is actually a paraboloid. Would you agree that this ball is the generalization of your parabola in 3-dimensional space, right? With the error as the y-axis, theta naught, theta 1 is the other 2 axes, parameter axis, right? You call this the hypothesis space or the parameter space. And the error forms a surface which looks like this. And this surface will be somewhere above the ground. That would be the measure of minimum error. That is, at most, you can come this far down, right? That's about it. So that is the concept. And therefore, so now look at this paraboloid. Suppose you make a guess. You randomly make a guess. You take some random value of theta naught, theta 1, right? You know that corresponds to some line in real data space, isn't it, guys? It is some line, and that line is probably a bad hypothesis, right? Because that line maps to very high error. what do you want to do in this parameter space? You want to go down to that point where the bottom of the bowl projects a shadow, isn't it? The bottom of this bowl, error bowl, projects a shadow on the ground. Right? So let that point, and that point would be theta, let me just call it theta star, made up of theta naught star, the best possible theta naught, the best possible theta 1, the best possible slope, and the best possible intercept. Would you agree with this idea? Isn't it? Now the whole question is, so machine learning, therefore, is to start with a bad hypothesis. Let me just say, this is the learning journey of machine learning. Do we agree, guys? Do you see how it is? That if somehow we could go from a bad hypothesis to a good hypothesis, which you don't know, the machine doesn't know. How could it do that? So what it could do is, the process is called gradient descent. So think about it this way. Look at this space here, which is the direction of steepest descent. It is steep like this, right? And when you project this vector, the steepness is maximum in this direction. Are we together, guys? Look at this. At this point, if I just go down, right? If I go from here to here, this vector projects on the ground to a certain direction. That direction would certainly point towards the minima, isn't it? So what I can do is this direction, the steepest, let me call this the steepest decline or descent. And the steepest descent direction projected onto the ground will point that vector, that thing on the ground will point in a direction that is taking us home, taking us toward a better hypothesis, isn't it? So imagine that look at this red little vector that I have drawn. This vector here, suppose I make a small step in that direction. Suppose my initial value of theta naught was whatever it was, and I take a small step, a tiny step, I'll call it alpha, tiny step in the direction, in this direction, this little arrow direction, then would you agree that I will end up with, this would become a theta naught better. It will be a better hypothesis, isn't it? In the same way, if I do the same thing with alpha, if I just go in the direction, a little bit in the direction, right, I will get a theta 1, which is a little bit better, right? In other words, I will end up at this point, a better point. Does that make sense, guys? You end up with a better point. And then what do I need to do? Keep repeating this. But remember, take tiny steps. So when you're learning, imagine that you are a centipede. Well, centipedes don't have giraffe feet, they have tiny feet, right? So you make tiny steps in the direction that is steepest, right? The steepest where? In the bowl, in the error surface. And you keep making little steps along this. But as you do this, you notice that if you're thinking in terms of the bowl, you're descending the bowl to here, to the minimum point, right? And you will end up at the best hypothesis. Guys, did this argument make sense? I'll repeat, it's very simple. What you do is at any point think, what is the steepest direction? And go in the steepest direction. Now, it just so happens, it's a mathematical fact, which I will just lay it here without explanation, that the steepest direction, this direction that we marked here, it is given by something called the derivative of the error function, generalized to higher dimensions. It's called the gradient. The gradient is a fancy name for the derivative of a multivariate function, because the error function depends both on theta 0 and theta 1, isn't it? And it is just made up of partial derivatives. Just as you would imagine, it is made up of d error, d theta naught, and d error, d theta 1, right? It's just a vector made out of this. So this arrow is actually this. And so the rule of learning is theta better is nothing but theta minus. Now what happens is that actually there is a minus sign involved. I'll tell you why. Actually, this derivative points in the direction of maximum increase. But do we want to climb up or climb down? We want to climb down. So you have to put a minus sign here, which is why this arrow, this is the truth. And so this equation becomes, okay, I should write it somewhere else. Let me write it in the next space here. And therefore you come to the celebrated equation that is the heart of AI, that is the learning in the machine learning. It is that theta beta, where am I? Theta beta is come to by whatever your previous value of theta is minus alpha gradient of E. Right now, alpha is a tiny step. This what I call tiny step, or the step of a centipede. People don't use the word tiny step and centipede. They use a slightly fancier jargon. They call it the learning rate. It is like how big your feet is, how big a hop you're taking. Generally, it's a bad idea in machine learning to be impatient and take giant steps. Why? Because you might overstep the answer and end up on the other side. It's like a train that's coming to a station. If it doesn't slow down, it will just shoot past it. Right? So it's best to take tiny steps. Right? And this celebrated equation is called gradient descent of learning. So if I take a tiny step, I end up somewhere and then I repeat and I keep repeating. But till when do I keep repeating? It turns out that at the bottom of the error, what is it? It's flat. Right? Is there a slope at the bottom? There is no slope. Like, for example, when you climb down Yosemite Valley, Yosemite Hill mountain, or the hillside, and you are in the Yosemite Valley, it's flat. There's no slope there. What does that mean? You will eventually, if you keep on repeating this gradient descent step, you will essentially have to stop because you will reach a point at which this will become zero. The gradient will become zero, flat surface. Flat surface means you're looking at a point in the hypothesis space, parameter space, such that if you move a little bit here or there, error doesn't change. Right? You have reached your home, you have reached your destination. So therefore, to summarize, there is a way to quantify errors, and there is a mathematical way to efficiently reduce the errors so that you can find the best model possible. Right? And because these things happen today on modern computers with their gazillions of transistors and petaflops of operation, today the marvels are that most of the time a self-driven car reacts much faster than you can. Many of you have accident avoidance in your cars, isn't it? If you're not paying attention and you're about to hit the guy in front of you, the new cars immediately brake on your behalf and protect you. How does it happen? Because the reaction time of the machine, it is calculating continuously what is the probability of having an accident, right? And the moment it realizes that an accident is unavoidable if we continue the current course, then avoidance mechanism kicks in and it reacts. Right? But it is doing those estimations in real time. Right? That if you keep driving at this pace, you're likely to hit the guy in front. Right? That's the power of machine learning. So machine learning happens because not only do the machines learn, but they actually have a way through gradient descent to learn broadly, very, very efficiently. Right? And so today we learned two things. I would end the theory part here because I want to give the second half after the break to the lab, right, to show these things in real example. And I will show you gradient descent. Now, to summarize, what did we learn? Regression is fx belonging to a number. It predicts a number. It's a model that predicts a number, right? Or more visually, x goes in, input goes in, prediction comes out. Y hat. If you know the ground truth, you can use that to train the machine to make a better hypothesis, better model. This is your regression model. We also know that we can quantify the errors. It's very easy. One way of quantifying the error is y minus y hat squared, sum over all the errors and average it, which is basically average of the error squared, right? Mean squared errors. One of the most popular ways of quantifying errors in a machine. You start with that, you make a random guess, machine makes a random guess, and then it improves. It has a systematic way to go decrease it through gradient descent in the error surface, in the error surface, right? Error surface being this bowl. Okay? And that, folks, is regression. I'll take questions before we go on to a break. If anybody has a question or would like to ask something, please do ask, right? So this is what we talked about today. Regression, it's a form of supervised learning. Regression, the model is internally some parameters. We learned about the Gauss-Markov theorem that says squaring an error is a better idea than just taking absolute values of errors and adding it up. Most of the time, not always, most of the time. Then we learned about the error surface and the fact that the error surface for a linear regression, that is when we try to estimate using a line, is quadratic. And so in this very simple case, we saw the value of gradient descent. Questions, guys? Any questions? Anybody? Oh, lots of messages. At what time classification becomes regression? Oh, Jagger. See, no, the way you say it is that if you're predicting into a finite set, it's classification. If you're predicting into a real number line or a vector, like basically Euclidean space, more generally, a vector, then it's regression. And you always distinguish between the two. A number line is infinite, or any number, a number has infinite possibilities, whereas classification, you presume that it's a finite set. And to your question, actually, once the category becomes too big, your classification models actually have trouble learning anything at all. You need way too much data to teach it anything. So Eric's question, in math, we say a function of x or a function of temperature. Would we call this a regression model of x? No, the regression model is the function. The function and the regression model are synonymous. And you can say a regression model of temperature or a regression model of x. Both would be correct statements. So you are right. No error. Following. Any other questions, guys? Any other doubts before we take a break? So let's take a 10-minute break, and then we'll shift our pace and go to the second part, in which I'll show you some examples in code. So guys, what I want to do now is show you a few examples of regression. And this should centralize on whatever things we have been talking about in the last hour. Before I do that, I wanted to show you the beauty of center limit theorem that I talked about the last time, the day before yesterday. This is, so if you remember, center limit theorem says that irrespective of the underlying distribution, if you take samples, lots and lots of samples, and you take something like an average or from that, then the average of those averages will go towards the right place. Right? That is one of the statements. And I'm deliberately being rather imprecise in stating it in all its full glory. There are some technicalities. When you take a sample, simple rule is common sense applies, namely to get truly random sample, right? Not the way political polls are taken. So if I want to prove that the current leader is doing a bad job, I deliberately go to a population that doesn't like that leader and then poll them. That's not a good sample. Right? Or if I want to praise the current leader, I deliberately go to the supporters of that leader and poll them. That's not what you do. The opposite of that is the word that the word is IID in statistics. It's a technical term. Fairness or common sense in statistics is called IID for sampling. It says independent and identically distributed. Means when you take samples, So if I took you, doesn't mean that therefore, because I took you, therefore I'll take your brother, right? Every element should be independently picked in a sample, randomly picked. And you should make an effort that this sample's distribution is as close as possible to the unknown population distribution, even if you don't know that distribution, isn't it? So basically, a good random selector will help you do the job. A good random function will help you do the job. So that is IID, right? And there is a point that when you take a sample, it is the replacement and so forth. So for example, if I take one sample and the people who are in the sample, it isn't that they're excluded from the next sample. They might also qualify. So you say sampling with replacement back into. So for example, if I sample from this jar, I take, let's say, these many, I took 5 stones and I want to compute the average weight of the stones. I can weigh these stones divided by 5, but then it doesn't mean that I keep them away. It means you put them back and pick up the jar again, and you take another sample, which is another 5 stones, right? And you keep doing it like that. So sampling with replacement and independent and identically distributed means make your best effort to be as fair, as close to the underlying population or representative of the population as possible, right? So common sense applies. So now suppose you're looking at people's heights, which you know sort of has a bell curve distribution. If you take random samples of people and you compute their averages, means of those random samples, you will notice that those, so here we took about 100 samples. You notice that those, what is the mean of the samples? It's around 0, isn't it? Right? And what was the mean of the bell curve? It was also around 0. Now you say that, well, that sounds suspicious. You deliberately took a bell curve, sampled off it, and then you're saying the average of the samples also is pointing in that direction. So let's do something else. We take a number, uniform number. You see that these are random numbers, uniformly distributed from 0 to 1. More or less, you see the frequency of each of the numbers is more or less the same. The y-axis is 10,000, right? So more or less, even though it looks a little bit jagged, that is because of random sampling, just to show. So now, what is the average? These numbers go from 0 to 1. More or less the same population, uniform distribution. So the average is 0.5, right? So what we will do is we'll take lots and lots of samples from this uniform distribution, and we will see what is the average of those. Look at that. The averages form a bell curve, isn't it? Centered around the correct value, 0.5, right? So it's remarkable actually how it happens. And you say, well, I'm still not convinced. Let me take a distribution that is like this, right? And I will find this distribution, and I'll print out the mean of this distribution, which happens to be 0.16. And now, what happens if I sample and do it? And when you sample and do it, you realize that that is exactly what it comes out to be, 0.166. I think that's what it was, 0.166167 is where all these means, the mean of means is pointing to, isn't it? Right? Isn't it remarkable? Actually, it's even if you take a very weird distribution like this is called the bathtub distribution, or more formally the beta distribution. Right? Again, the same thing happens. And isn't it miraculous that when you take averages, samples and their averages, no matter what distribution you take, average of average always takes you to the right answer. And it shows a bell curve distribution in itself. That is the famous central limit theorem, and it is essential, otherwise you wouldn't be able to do machine learning. Now, this was just a recap of what we did last time. It's one of those beautiful results. If you think a little bit about it, you'll be amazed that it is true at all. Now, let me show you something else. I encourage you to do, I want to show you today, I taught you gradient descent, which is how machines learned. Right? So we take this data, this is real world data. Let's take a real world example. Most of you have been to the Yellowstone National Park. and you have met the old faithful geyser. As you know, it erupts every once in a while. But if you observe the eruptions of the old faithful geyser, you will notice that when it erupts, the longer the eruption happens, the longer you see the water come out and steam come out, the longer you have to wait for the next eruption. Right? Why? Because geothermally, it has exhausted its energy. It needs to regain that energy for the next eruption. Right? And so this is a plot. Eruption is how long, x-axis is how long the eruption happened, and y-axis is, well, therefore, how long you have to wait for the next eruption. You can see that there's a linear relationship, right? You should be able to predict, roughly speaking, how long you have to wait based on the length of the previous eruption. And so you can build a model. We will build a model through this. Instead of theta, I've used betas here. I won't go through this code because it is exactly the code that we wrote. Maybe I will go through. Let me go through this, guys. Do you see this equation? Beta next is, I'm writing it here in terms of beta, but if I were writing it as theta, isn't it? Theta beta is the previous value of theta minus alpha, the gradient of the error. This script L is the error. That is what it is, isn't it? And you can work it out. It's quadratic in that. And so quadratic equations have a particular shape. Then when you work out the mechanics of this equation, this is what it turns out to be. You can write it in very simple Python code, which I won't do here. So you notice that this is the Python code, alpha, beta naught, beta 1. You can compute the gradients, and you can compute the loss and updates. And so you can take tiny little steps, and beta naught, beta 1 improves. So it goes from 3.891 ultimately to 0.016. And beta 1, the slope goes from some random number 4 down to 0.91, close to 1. Right? If we look at this data, yeah, let's see if it makes sense. If we imagine a straight line going through, would you agree that more or less that straight line, imagine from here going through, that when you rise up by 1 unit, you go from, like, see, along the x-axis, you go 1 unit, you reach here. At this moment, the y also seems to be more or less 1, or a little bit less than 1. So if you go 1 unit x and you go just a little bit less than 1 unit up, it means your slope is just a little bit less than 1, isn't it? Which is what the machine seems to have discovered by learning, by taking tiny little steps all the way, 200 tiny little steps. It is coming to the conclusion that the slope is 0.91, right? Very close. Now, what happens is if you plot this, you can see that beta naught, it learns, you take with a random value 4, beta naught, step by step, all these things machine learns, it ultimately ends up with, at 200 epochs, it ends up with the value close to 0. It says, well, it's close to 0. And beta 1, you go and it asymptotes to close to 0.9 here. And this is the loss. What is happening? The error in the beginning is quite high, but as the machine learns, it's making smaller and smaller mistakes. It's making smaller and smaller and smaller and smaller and smaller mistakes. Finally, it reaches a point at which basically it's making as little mistake as possible, right? And that is machine learning. You can think these are the contour lines. Each line tells you how much mistakes are being made. Obviously, you're going towards the center of the line, which is best illustrated with this. See, we started here, this random point. I deliberately took that random point. This is the error surface. Do you see this beautiful surface, guys? This is the error surface. Right? You make a random guess at this point, at the tip where my mouse is. Here, the error rises up to this value. Now what do? You start doing gradient descent. Guys, do you see that this is the path of steepest descent in the valley, to the valley? That is why it's called gradient. Gradient implies steepest, right? Steepest descent path. And when you look at the shadow of it on the ground in the parameter space, you notice that it is the shortest path to the best answer. In fact, it makes an arrow like straight path to the right answer. And that is machine learning, guys. This is machine learning. You can see it actually. Let me see if I can run this visualization, this video. Let's try running this video. Oh no, this video is we have. So this video we are going to watch, which has come, by the way, the code for the video. How did I generate the video? The code is right here. It was actually it was Kyle, one of our AI engineers in our team who made this video. So we are going to run this video now. Let's see. You see it doing gradient descent, right? Do you see it, guys? Let me go here and stop. You see that the point you have gone from this point, come down to here. In the parameter space, when you look at the projection on the ground, you have gone from here to here. Now see how well and sure-footed the learning is. And that you are literally seeing the machine learning in action in this particular visualization. Right? This is real, by the way. This is not just some fancy animation. It's literally derived from the math that we just did a little while ago. Yeah. And let's now go back to how, I'll just take some examples and see. Let's see what are some simple examples, because this is a simple class. Classifier lesson 12. Okay. Let's look at this. Suppose reality presents to you like this. Can you immediately see the right relationship? It's a straight line relationship, isn't it? You can build a regression model. Let's see if the machine is able to discover it. I plotted the points. Then you build a regression model. By the way, making a regression model in Python is very, very easy using the scikit library. It's very simple. Okay? And I'll go over the code as a hands-on, probably not in this series, but in a subsequent series or subsequent evenings. I will. We can do this session in which I can bring you up to speed with scikit-learn and this Python libraries. But suffice is to say that these are very, very easy things to do. And you notice that it is learning the slope, etc. Well, this is residual analysis. It's a little technical. We won't go into that. But look at the prediction line, the model. Would you agree that this is a good model for this data? Right? That is that. Then let's take a slightly harder data set. Let's say, now the relationship is not linear. You can't fit a line to the data. You need a little bit more sophisticated model. If you try to fit a line, you will look rather clumsy. For example, would you think that this dark maroon line is a good model of the data? It's not at all a good model of the data. And actually, the way it manifests itself is what is called the residual plots. If you see a pattern in the residual plot, it means that you have basically screwed up, right? But we won't go there. But now let's look at the other model. What do you think of this model? It does seem to be a much better model, right? Not a perfect model, but a much better model. Right? And so how do you know that it's a good model? First, by superimposing, also by looking at the residual plot. And you notice that remember this, look at this residual plot. Do you see a very obvious pattern in the data? And you don't see that kind of obvious pattern in this data. So that's how you know that you do have a good model. So we can do a few more examples. Let's look at what data set 6 is. Oh, this looks hard, isn't it? Look at the snake-like data. Can you model that? Of course, modern machines, modern algorithms are pretty smart. If you try to do it with a line, it's hopeless. See, this is the best line approximation. See, it may sometimes be useful if all you need is a rough and ready model that gives you a very rough estimate of y based on x. This model isn't doing so badly after all, isn't it? Then, but if you try to make a better model, you would agree that this is a better model. Right? Then you could do even better. Oh, what about this? It's better. But beware, when you use, in this particular case, you use polynomial regression, you realize that around the tail end, you have a bit of a problem. It is sort of over fitting to the data, right, at the tail edge. Both the tails sometimes overfits, and this phenomenon was discovered by the mathematician Runge. That's why it's called the Runge phenomenon, or I call it the wagging tail. Those of you who have a dog would appreciate that. This is a wagging tail phenomenon, right? Because if you extrapolate from this data, you can see that it's just making garbage predictions beyond this. And here also the tail gets pronounced. But so beware when you build an overcomplicated model, it may have limitations, or you should understand the limitations of the model. How we do that is a little bit, that's where you actually come and join our courses. And we at this moment, I just wanted to give you a taste of what regression is. So folks, that is that. It's 9 o'clock. What I would like to do is, any questions, guys, before I go through the setup and so forth? Any comments? Yeah, go ahead.
So we saw different, like normal regression and then polynomial regression. So my guess is, depending upon what kind of regression one would choose depends upon the data they are going to analyze first. Is that correct?
That is right. See, what happens is that within the regression family, there are lots of models. There are linear regression, nonlinear regression, polynomial regression. There is, then there are ensemble-based methods like random forest regression, gradient boosting regression. Then there are kernel method regression, things like support vector machines. Actually, this company is named after SupportVectors. That's why it's called SupportVectors. It's one of the algorithms. Then you can use neural networks. And some of these are more expressive than others. For example, a neural network is what is called a universal approximator, which means no matter how complicated it is, it will find a way to model it. The downside is when your data is very simple, you're just burning a lot of computes to do something obvious. So which model you pick, you're right, has to be data dependent. You see, this field is about, it's a scientific discipline. You ask, you hypothesize that this will work, try it out. If it doesn't work, you try something else. Any other questions, guys? There was another little example one of our people did, is you look at these moringa leaves. Right? So suppose you ask this question, and this was actually one of our students who did it. We gave them as an exercise. We said, okay, go measure the length, the size of the leaf, and the size, how long it is, and how many leaves does it have? And can you predict how many leaves will it have? And here is a beautiful, she did a beautiful analysis. She's in the audience at this moment, actually. And she built this model, which you would agree is a pretty good model, right? Even though the data is nonlinear. So people have a lot of fun, actually. See, with AI, it is not a spectator sport. Much of the fun is in doing it. It's a lot of fun. It's a whole lot more fun being on the tennis court playing tennis than just watching it on TV. And certainly very, very true of AI. It's a beautiful discipline. So guys, next time we'll do classification. Tomorrow we'll do classification. But for today, this is the end of it.